we will have a test for this course on this day. Okay, it will be on next Monday from 10 to 11:30. So it is July 1st. And depending upon how you do, you will get a grade A, B, C, D. And then for the test, you can use the printout that you have. You can use it during the exam, but you cannot talk to each other or use your cell phone to find the answer. The answer, you should take it out of the lecture notes that are already given. You have any questions? So next Monday, so 10 to 11:30, and you can use, but nothing else. Only the, if you have a book, you can use the book. Otherwise, this should be enough. Okay. Now, I want to talk a little bit about what is photochemistry, what is the chemistry that you learn every day. Okay. So, in photochemistry, we try to understand how the light interacts with molecules or materials and what are the consequences. So there are several types of photochemistry depending upon what type of molecules you deal with. Something is called as organic photochemistry or inorganic photochemistry or photobiology. Okay, all of them contains, as you see here, there is a photo, and photo. And then if you are dealing with organic molecules, it will be called as organic photochemistry. For example, if you are dealing with still beans, benzene, or benzophenols, that part of the chemistry is called as organic photochemistry. The principles are the same, but the type of transitions involved could be slightly different. Inorganic photochemistry is the same principles, but you deal with molecules like ruthenium, cobalt complexes, or these types of bigger molecules. Photobiology deals with chemistry of big biological systems. Like yesterday we talked about vision, or for example photosynthesis. They are photobiology because it is dealing with bigger molecules. Things are a little bit more complicated, but the main thing is the light interacting with the molecules. So the principles that we talk about is the same whether it is biology, inorganic or organic. Okay. Okay, you already know a lot of chemistry. And in the chemistry that we have learned at this level, it all deals with molecules activated by heat. Okay. So what we do is, in the lab, you heat something and then the molecules gets activated, they undergo chemical reactions. That is everyday chemistry. In photochemistry, the molecules are not activated by heat, they are activated by light. So the reactions will be at room temperature, but then you shine light on the compound, the molecules will get activated, and then you see chemical reactions. So that is what is called as photochemistry. So there is a difference between thermal chemistry and photochemistry. Thermal means heat, photo means light. So the same molecules, either you have to make them react. To make them react, you use in one case you use heat, in the other case you use light. But the principles are very different. When you heat a molecule and when you activate it with the light, the way the reactions take place are different. So that's what we want to learn something about photochemistry. Okay. So the difference between thermal chemistry and photochemistry comes from the fact that when you heat a molecule, the whole molecule gets hot. When you shine light on a molecule, only the parts that absorb the light that will get activated. So the reactions that are activated by light is very selective compared to the reactions by heat. Okay. So when you heat a molecule, that is, you put them in a furnace or in a beaker and then on a heating mantle, the entire molecule will get hot. So either this piece can come out, or some other piece can come out, or the head can come out. Anything can happen to the molecule. On the other hand, when you activate the molecule with light, not all parts of the molecule will absorb the light. Only some parts of the molecule will absorb. And that part is the only one that will react, not the entire molecule. Okay. That is the big advantage of photochemistry. Okay. So when we talk about thermal reactions, the reactions, molecules have vibrations. So if you have a molecule, they are always doing like this. So when you heat it, it will vibrate a little bit more, and if you heat it more, it will go a lot more, and eventually will break. Okay. So the reactions that proceed by heat, it is essentially controlled by vibrations between two atoms. If you talk of a molecule, it is made up of several bonds, and all the bonds will be vibrating at room temperature. If you heat it, they will vibrate more and more and more, and eventually when you heat very high, then it will completely break. On the other hand, when you do the reaction by light, it is not the vibration, the molecule when it is vibrating, when you shine light on this, the vibrations does not change. But the electrons move from one orbital to a different orbital. So there is a change in the electronic configuration which will change the reactivity of the molecule. So the heat, it activates vibrations. Light, it activates the electronic configurations. So these two are different. So because of this, you need to understand how the light interacts with the electrons. And that interactions will lead the electrons to go from one place to a different place. And once it goes to some other place, then it will control the molecule. That is what is photochemistry. Okay. Is it clear? So, you think, tell me, when you heat a molecule and when you activate the molecule with the light, what is the main difference between the two? There are, I have listed here, but the most important difference between the two, what exactly is this? When you heat and when you shine light. You can tell in Chinese, somebody else can translate it in English. What is the difference between the two? I just not told you.
The difference is just for the energy, but vibration and electrons.
Okay. So the difference is between, in one case, the heat activates the vibrations. In the other case, it activates the electrons, not the vibrations. The electronic configuration is different from the vibrations. Vibrations are only the nuclei. If there are two atoms connected, they are connected by a bond, and then they just vibrate like this. And then these connections are held by electrons. And when you shine the light, these electrons go from here to here. So when they go, they weaken this bond. So you don't have to do heat. So you can just activate it by light. That is the principal difference between the two. But this requires that you need to understand how the light activates the electrons. Where does the electron go? So when you shine light on a compound, the electrons will absorb the light. It will go somewhere. So we need to know where it is going, and wherever it goes, how does it alter the chemistry of the molecule. So in your, when you study chemistry, organic chemistry or physical chemistry or any one of these things, you have a picture in your head how a chemical reaction takes place, right? So if you have this is the reactant, this is the place where the reaction starts, and this is the place where the reaction stops. This is the starting point, this is the end point. Here the structure is a reactant, here the structure is the product. So if you take one molecule here, if you keep on heating it, it will just break some bonds and then it will go to something else. So something else is the product, this is the starting material. So to go from here to here, you have to break some bonds. Breaking the bonds, that involves heating. And do you know, I'm pretty sure you know, what is a transition state in a chemical reactions? Do you know what is a transition state? I don't know what that, no? Okay. Activation energy, do you know what is activation energy? Okay. So, here, this is the reaction where it starts, and then the product is here. So the product is more stable than the starting material. Although it is more stable than this, it doesn't mean it will come straight from, it is easy to go. To go from here to here, it is not that easy to go from this place to that place. So for example, if you have from this building to another building, if you have to go, if it is downhill, it is easy to go down. If there is a small barrier, then you will have to go up and then come down. So every reaction will have a barrier, because if this is more stable, this is the reactant and this is the product. Although the product is more stable and it is built with a small hill connecting these two. That hill is called as, top of the hill is called as transition state. So the transition state, you have to cross this place to come down here. So you keep going up and up and up. Once you go up, then you come down. Coming down, it doesn't need energy. Going up, it needs energy. So that is what happens in thermal reactions. So you supply heat, the molecule picks up the vibrations and slowly climbs the hill and goes up and goes to the top, and from there it will come down. So this is what is called as the activation energy for a chemical reaction. So the activation energy is basically from here to here. That is the activation energy, and this peak is called as transition state. In any chemical reactions, thermal reactions, you will have to supply this much of energy, and that much of energy is the barrier for the reaction. So it will change from one reaction to another reaction. Okay. So this is the way thermal reactions work. When you think of a thermal reaction, if you go and read a book, they will have this picture. This is very common. So you think of them, this is the reactant, this is the product, this one is called as reaction coordinate. So this part of the picture is for thermal reactions. For thermal reactions, if you have a reactor here and if you heat it, it will cross through the barrier and then come down here. Same thing will happen here. This surface is called as ground state surface. Ground state means that is the most stable electronic configurations of the molecule. Okay? But when you activate this molecule, what will happen? If you shine light on the molecule will go from here to here. That is the excited state. That is what photochemistry is all about. So in the excited state, as the molecule goes from here, okay, you have to understand, in the ground state, this is the ground state, you have the reaction, you have the product. So to go from here to here, you go up and then come down. Whereas in the excited state, you take the molecule from here to this place, and to come here, you just directly go down. So that is what is the, these are called as diabatic reaction. That means the reaction is taking place on two different surfaces. That is the excited part of it and the ground state. It is like going from here to, let's say, Chengdu. When you go by train, okay? If you go by train, it is going to be like this. You go through here and then go up and then come down. Or you can take a aeroplane. In that case, you go from here, go up, and then you go down very quickly. So the reaction will be faster. Whereas when you go by train, it is going to be slow because it is going to be go through the surface. Whereas in the excited state, you just start from here, go up, and then it just lands in Chengdu maybe in 2 hours, or I don't know how long does it take. The train may be like 4 hours, so it's a much longer time. Okay, but the two things are very different: going by train or going by plane. So one goes up and then comes down, and another one it just keeps going on the ground. So that means it takes longer. If there's a problem, then the reaction will be very slow. Okay, so this is the way how you think about a reaction in the excited state. Okay, so this is something important you have to know. So tell me, in the thermal reactions, what is the most important point that you have to cross? In the excited state reaction, what is the most important thing? How does the reaction take place? You can tell in one sentence or two sentences or what? Tell me what is the difference between the two types of reactions? You know, you can tell. I don't think you have to speak perfect English. If you tell in some few words you add, I will put together a sentence. So will you say something? No? Okay. Everybody? So in thermal reactions, what is the most important the barrier that you have to cross? No? Maybe some of you can come and sit in the front so that I can hear you, or you will be more under a lot of you have more pressure to say something. Okay, in thermal reactions, you go through here, that is the transition state. In a photochemical reactions, see, this is the part that light will help. So it takes the molecule directly from here to the top. In one step, it will take it from here to here. But once it is here, the electronic configuration is very different from the ground state. But then, once it is different, it wants to come back to the old ground state, electronic configurations. When it does want to come back, it will come down like this. When it does come down, either if it comes back here or it comes back here, depending on that, you will get the reaction or you will get a fluorescence. Okay? Alright, so these are some simple things. There are some basic rules. These are very basic. Okay? But many times the basic rules people don't understand. And then they do things which are not right. Another thing is called as, these are the two people who put together for a photochemical reactions to take place. The light must be absorbed by the compound. Many people I have seen, I was, as I mentioned to you, I was in Shanghai a few days ago, and they were discussing, the students were discussing with me some reactions. And then he said, I irradiated the compound, I don't get the product. And then I was talking to him, where was he irradiating? Some 300 nanometers. Where does the compound absorb? 500 nanometers. So if your compound is absorbing at 500, and if you're irradiating at 300, there will be no reactions. Because each compound has an absorption spectrum. And only in that particular region, the molecule will absorb the light. So you will have to, if you want to do fluorescence or chemical reactions, you will have to excite the compound in the right region where the molecule absorbs. So this is the basic rule put together by Rother and Robert. And it's very obvious, you don't have to be a genius to figure this out. But even today, very many people, they don't understand. They think that photochemistry will do anything. It doesn't do anything. Unless the first law of photochemistry is light must be absorbed for photochemistry to take place. If it does not absorb, there is no photochemistry. Okay. And the second law is due to Einstein and Stark. This is also very important. But these are all very simple rules. But simple rules, if you don't follow, things don't work. Okay. So the second law of the photochemistry, each photon of light absorbed by a chemical system, only one molecule is activated for a photochemical reactions. Okay. So this is also very important. If the light, yesterday I mentioned it to you, it comes as in units, like photons. They are called as 1 photon, 2 photon, 3 photon, like that. Like a molecule that you count, 1 molecule, 2 second molecule, 3rd molecule, 4th molecule, and then you can add on like this. Light also, when it comes out, it comes in 1, 2, 3, 4 like that. Although it doesn't look like it, but when it from the bulb that comes out, it comes out as 1, 2, 3, 4, 5. And you can count the number of photons. So each molecule will absorb only 1 photon. So if you have 1 molecule and then you keep on irradiating, doesn't mean it will absorb 5 photons. So if you have 100 molecules, you want them to react, you have to have 100 photons. If you have 20 photons and you want 100 molecules to react, you will then only 20 molecules will be reacting. 80 molecules will not react. Okay. So here, so each photon of light absorbed by a chemical system, only 1 molecule is activated for a photochemical reaction. So only one of this 1 molecule per photon will react. That is what these two people said. This is true. Because otherwise what happens is, even today, people think that just by increasing the intensity of the lamp, you make it brighter and brighter and brighter, you are going to get a lot of reactions. No. Because it depends upon the fact. If you make it brighter, it doesn't mean number of photons are increasing. It is the intensity is increasing, but not the number wise it remains the same. Okay. Now we keep up. So all of this photochemistry is now only about photons and a molecule. These are the two things, the key things in the chemistry. Photon is a light. Molecules are, we know what is a molecule. A photon and a molecule, they interact. And when they interact, the light completely goes into the molecule, disappears. And when it does disappear, it does something to this molecule. When it does something to this molecule, we want to know what it does, and that is what the whole thing is going to be about. Okay. So, for example, you want to know what is a photon, that is we call what is the light. Okay. And then what exactly is a molecule? When you say a molecule, like methane, CH4, or benzene, C6H6. Okay. So we know what is benzene, we can write, but exactly we don't know what it looks like. But we need to know what it looks like for it to figure out when the photon interacts with the benzene, what happens to benzene. Okay. And we also want to know when they do interact, when light and the molecule they interact, how do they interact? What exactly the interaction means? We want to know. Okay. And when this photon and this one they just collapse, what exactly happens? Okay. These are the things that we want to ask, we want to understand. If you really want to know what happens to the molecule after absorption of light, we need to understand each one of these things. Okay. Question? Okay. All right. So yesterday I mentioned a little bit about what is light. So we need to have some knowledge. What exactly is light is a lot more physics than chemistry. So, but we as a chemist, we need to have some feeling for things. We cannot say that I don't know physics, so I don't want to know anything about light. But so the light over a period of time, about 2000, like almost 3000 years ago, to today, there has been some understanding of what exactly it is. So we said it can be a particles or it can be a wave. These are the two concepts that are evaluated, that have come out over the last 2,500 years. So people keep asking, questions. What exactly is light? You look at the light, you come to the room and turn on the lights, but we don't understand what is the light. Okay. And for some people, they worry about it. Most of us, we don't worry about it. When the light comes on, we are happy. When it is dark, we are unhappy. So these people, so Newton, he thought light is like a sand is a lot of particles. And the Maxwell, he felt it's not like a sand, it's more like a water waves, or it's like a wave. So these two are totally different concepts. So one guy says the light that comes from there is like a lot of particles are coming out. The other guy is saying all the waves are coming out of this light. What is, depending upon how you think, that is very important to know, because if this light is going to interact with this molecule, is it a particle or is it a wave? When it comes and hits this thing, is it looks like a particle or it looks like a wave? So these are two different things. So we need to know what exactly these are. Okay. So the main person was Maxwell. He said the light is more like a wave. And then when you have a wave, if you have gone to a swimming pool or some big lakes, you will see waves. Waves can be very quick or it can be very slow. Okay. So depending on if you think light is a wave, it will have a wavelength. So the waves can go slow like this. So or the waves can go very quickly. So how do you know whether the light that comes out of this projector, is it like this or is it like that? So to figure out that, it depends upon if you stand here and then watch this coming towards you, this one will come and it will take some 5 minutes for the next one to show up. So this distance between this and that is called as wavelength. Okay. And then if you go to this one, if you stand here and then if you look at the wave, this one will come very quick, one after another very quick. So the distance in this one is also wavelength. So it depends upon the light. If it comes very quickly, then that means a shorter wavelength. If it takes a long time to come one after another, that means a longer wavelength. It is like, if you have something like this, a saw with, if you want to cut something, you use a saw. And then there will be a blade. That blade can be far apart or it can be very, very close. So if it is very, very close, if you cut it, it will fall. You can cut more easily. If it is far apart, then you will have to keep cutting longer time. So the light is, so the frequency That is, when you do this, how much you have to do, it depends upon the distance between, if you have this saw, sometimes you will see on the saw, the blade will be there. That blade will have something like this, that is what is going to cut. So that one, if it is far apart, then it has a longer wavelength, and then it is going to come, and then one after another it will be taking longer time. If it is very quick, then you can just do like this, and then it will cut the things, the root or whatever faster. So they are measured in terms of wavelength or in frequency. Okay. So the light, when you tell something, like when you say a molecule, you say atomic, you tell its radius, you tell what is the weight of this molecule. So in the case of light, you tell what is the wavelength. That is what defines the light. When the wavelength is longer, the light will be colored. When it is shorter, there will be no color. It will be ultraviolet. So the wavelength decides whether it is going to be red, blue, or green, or it is going to be ultraviolet. So each one has a different wavelength. Okay? So these are some things that you have to know. C is the speed of light. How fast the light travels, it depends upon the wavelength. If it is coming slowly, then it will take from there to here longer time. If it is walking very quickly, then it can come from there to here much faster. So the speed of light depends upon, for example, the wavelength multiplied by frequency. Okay? So these are some. So from each photon, depending on the wavelength, it will look different color. The color that you see on your shirt or all of these things, it is coming from because your color, the shirt, it is fluorescing or absorbing some light, and that light, whatever is left, is the one that you see. Okay? So over a period of time, all of these people, they have made a lot of contributions, and then they figured out the light can be a particle or it can be a wave. It all depends upon if the light is coming and if you have a target. When it is coming, when it comes and collapses on this, it depends upon what is this one. If it is something very hard object, then it will act like a particle. If it is something like a soft object, it will act like a wave. So it can be either this or it can be that. So the light, you cannot say whether it is completely particle or it is completely waves. It depends upon with what it is interacting. So suddenly it can be this or that. Okay. That's why all these are all famous people. All these are, De Broglie, Niels Bohr, Einstein, Planck. They're all extraordinarily famous physicists who put together the ideas about what is light. Okay. So the light, what we say light is a common term. But most of the time we call them as photons. Photon is a little bit more technical terms. When you want to say a photon, you have to give some numbers for this. What are the various, what type of photon we're talking about. Okay. Photon or light is very general. Okay. Right? When I say Chinese, it can be any Chinese. Chinese students from Beijing or Shanghai or Xi'an or Chengdu, any of them, they are all called as Chinese. But students here, each one of you has a different name. So each one is very special. So you do specialize to point out so and so. I will say the name of this person and how tall she is, or how short, or fair, or dark, or what, all this defines all this stuff. So each photon that comes out of this projector has a different characteristics. So how do you decide which, if I tell somebody, bring me a projector with this kind of photon, then I will have to tell them, okay, maybe a blue color or something which is brighter, all these things I have to tell. Otherwise, I will get something which may not work. Okay, so when you say a photon, you define by wavelength. Wavelength is the one I told you. If there is a wave going through, then the distance between the peaks is called the wavelength. So it can be like this, or it can be like this. So then it will be shorter wavelength. If it is like this, it is another wavelength. So you can measure the distance and that is called as wavelength. Okay? And the wave number is when you stand here. If you look at these waves, how many waves pass through in a particular length of time, that is called as wave number. If it is going very slow, that will be slow. If it is going faster, like a small kid versus an old person will walk very slow. The kid will run. So if you stand here, then you will see this kid, the count will be much larger number of steps, whereas the other guy will go very slow. That is the wave number, frequency, and the energy. This is most important. Each photon that comes out of the projector, how much energy it has got, it depends upon h mu. Have you heard of this? Have you h mu? H is Planck's constant. Mu is the frequency. Frequency is basically the c over lambda. That is c, the speed of light, lambda is this one. The speed of light is fixed, lambda is, it can change. So h mu, how much each photon, how much energy it has got, it depends upon the wavelength. Because h is fixed, c is fixed, the only thing that is changing is the lambda. So if you have 500 nanometers or 300 nanometers, the energy of this photon is different. That's why if you go outside in the afternoon sun, there is more of UV light, so you feel it's very hot. And then in the evening, the light is softer because it has got more and more of the visible light. So now you don't feel that hot. Okay. So the energy that is directly proportional to h mu. So when you see in the chemical reactions, on top of it, people will put h mu. That means they are using light. If you really want to know how much what kind of h mu, then you have to know what is mu. Mu is c by lambda. Lambda will change from one projector. This projector, if you take some other projector with a different blue or green or red, the energies of each one will be different. Okay? And Einstein is the name of the person, but also Einstein is a unit. Tell me, what is Avogadro's number? Do you know what is Avogadro's number? What does Avogadro's number mean? You know Avogadro? You have heard of this guy? Avogadro. You must have heard. Okay. If you have come this far, you should know what is Avogadro. Avogadro's number. Avogadro is the guy. 1 mole of a molecule will 1 mole of anything will contain this the 6 in 10 to 23 number of molecules. 1 mole. 1 mole is how many molecules are there. Mole is different from molecule. Molecule is only one. A mole is some number of molecules is called as 1 mole. 1 Avogadro number of molecules will be 1 mole. That is 6 to the power of 6 in 10 to the power of 43. That is a very standard number. Okay. So similarly, if you have 1 mole of photons, that is n is the Avogadro number, 1 photon is h mu. If you have 6 in 10 to the power of 23 number of photons, that one is called Einstein. So if you have 1 Avogadro number of, or 1 mole of compound, if you want to activate all the molecules, then you will need 1 Einstein of photons. 1 Einstein is equivalent to Avogadro's number of photons. This is the common terms. When you read a book, they will tell you Einstein, Avogadro's number, all this stuff. Okay? And the speed of this light is 186,281 miles per second. From there to here, it is extraordinarily super fast. So the light that is travels from sun to here, it is coming at the speed of this 186,281 miles per second. Okay, this is faster compared to any kind of train or aeroplanes that we have. Okay, and also the the light, it has a momentum. Tell me whether the light that comes out of the projector has any charge. For example, electrons have charge, protons have charge, right? Electrons have minus charge. Proton, that is H plus, has a plus charge. Photon is H mu. Tell me, H mu has any charge or no charge? Charge means either plus or minus. Does it have a charge? So if you have, for example, a beaker full of electrons, that means each one is minus charge. So if you have 100 electrons, you have 100 times minus. Okay. If you have H plus, that is a proton. If you have a beaker full of 100 protons, you will have 100 plus charge. So if I have a beaker full of photons, will I have 0 charge, plus charge, or minus charge? 0 charge. So the photons that comes out of the projector has no charge. Although it doesn't have any charge, when it interacts with a molecule which contains minus and plus charge, it can interact with this, and then that can activate these electrons from one place to a different place. So it's very important to know that photons has no charge. Okay, if the protons, they have no charge, but then what is photons has a spin. The light that comes out of it, it can have a positive or negative spin. We don't worry about it because it has got 50-50. But it can be circularly right circular or left circularly polarized light. Light is, normally it is not polarized, but it can be polarized because light has got, for some reason, it has got left and right polarized. Okay. So when you say a photon, so these are all the various properties of a photon. So when you have a light that is going to interact with your molecule, you should know all of these things so that you can understand when it hits the molecule what it will do. Okay. Okay. So the light is also called as electromagnetic radiations. So the light is the same thing. Like some people, Chinese people have Chinese name and then Indian name, English name, and all this stuff. So it is all the same, but under different names. Okay. So it is also light or photon or electromagnetic radiation because it has electrical charge, electrical field, and also magnetic field. So that's why it is called electromagnetic. So the light, everything is light in a photon. That you hear the radio. That is a photon. And then you talk on the cell phone, and that is a photon. That is a sound, but it is a light. But depending upon the wavelength of the light, wavelength is the one that I told you, the peak positions, the first one and the second one, how far away it is. That is the wavelength. That wavelength makes a big difference in terms of energy of these photons. Energy is H mu. Mu is C by lambda. Lambda is on the bottom. So smaller the lambda, more is the energy. So smaller lambda means that the peaks are very close. If it is larger lambda means the peaks are far apart. Okay? So X-ray, ultraviolet, infrared, radio waves, and then microwave. Tell me which one is more energy in this one. Okay. So, for example, when you talk to a cell phone, we use microwave. Okay. When you take X-ray of your body, we use X-ray. So the energies of this microwave is very highly energetic. When you talk on a cell phone, your ear will fly off. Okay. But so that's why we don't use this very energetic radiations to communicate. The communications is done with smaller radio. That when the radio signals coming from one station to another station, it goes to the radio waves. For chemistry, we use mostly here. This is the ultraviolet, to the color. Each color is a different wavelength. Okay. So, for example, So X-ray, that is here. This one is extremely short wavelength. Then it will ionize the molecule. If you have X-ray bombarding in this room, then all of us will just slowly will go away, disappear. And then if you have a UV and visible, UV is ultraviolet, visible is all these colors. Visible is basically violet color, green color, red color, whatever color you have, they are all called visible. But that one is not, it is energetic, but it's not energetic enough to completely vaporize our skin. What will happen is, it has just enough energy to move the electrons from one orbital to another orbital. So that is used for electronic transitions. So now we need to understand what exactly is the electronic transition. The other one is infrared. You might have been taking spectra, infrared spectra. You might, for example, if you want to take, let's say, if you have an unknown compound, you want to find out what it is. One of the things that you will do is you take the IR spectrum, that is the infrared. The infrared, what happens is it produces a whole bunch of infrared radiation that is sufficient only to make the vibrations. So the molecule will have all kinds of hundreds of vibrations. Each one will require a different amount of energy. So when you take the infrared spectrum, you will see a lot of peaks. Each peak corresponds to different vibrations in the molecule. So the vibrations are the energies are only 5 kilocalories, 10 kilocalories like that. The electronic transitions are 50 to 200, so it's a lot more than the vibrations. And then microwave. Microwave is the one that we cook something at home. That is basically, if you use microwave, the molecules will rotate. Whereas when you use infrared, molecules will move. And then if you use radio frequency, in terms of chemistry, radio frequency is the one that we use for radio. But in the chemistry lab, we use it to change the electronic spin. So when you have, I don't know whether you use NMR machines. NMR is nuclear magnetic resonance. You use? If you're an organic chemist, you will use it every day. The NMR is record to find out the positions of hydrogens in a compound. So the NMR is basically the spin will change from alpha to beta. So that is a very tiny amount of energy. That is what we use it for, radio frequency. Okay? So depending upon the wavelength, the energies are different and what it can do are also different. Okay? So this is the various things. And for our purpose, in this course, we are going to be essentially trying to use the UV and visible. This is what will change the electrons from one orbital to a different orbital. Okay. And then, if you want to know how much energy a photon has, you need to know H and mu. H is a fixed number. You should memorize or you should look at a book. And then mu is, for example, it depends upon the C divided by lambda. So Hc is constant. H is the Planck's constant, C is the speed of light, both are fixed numbers. So basically if you convert them, it comes to this number here, 2.8 10 to the power 4 kilocalories. Divide by lambda, that will give you the energy for each photon. So if I have a torchlight with a torchlight of wavelength of 400 nanometers, and she has a torchlight of 200 nanometers, the energy, when I shine this, both of us are not exactly the same. The energy that comes out of these are very different. Okay. So for example, you take just for 700 nanometers, light, the energy is about 40 kilocalories. If you have 200 nanometers, the energy is about 143 kilocalories. Because we just, I don't know what kind of unit you use. In America we use mostly kilocalories like that, so that is much easier to. So if I tell you for 700 nanometers, 400 nanometers, you don't know what it is. If I tell you it is 40 kilocalories, 40 kilocalories like that, then you can imagine how much energy is needed to break a bond, whether I have sufficient energy for this. Okay. So for example, that means it is 400 nanometers. If you see a color red, it is 700 nanometers. So this color and that color, they have different amount of energy. This color is our 400. So if you put it at 400 here, you will get 71 kilocalories. You put 700 nanometers, you get 40 kilocalories. Okay. So the light with a different wavelengths will have different energy. So if you have a molecule with the different electronic configurations, how much gap is there, you will have to use exactly same amount of energy to populate the molecule from here to there, and figure out that you need to know the gap, and then you need to figure out what is the wavelength. Okay. So this is, in that sense, this is useful. Okay. Tell me if you have any questions. You have questions? Okay. No? I don't know whether I am a very excellent teacher, or you are afraid of talking in English, or I am a very poor teacher, you don't understand anything. So I think I will stop here for about maybe 10 minutes, so that you can at least feel better that I'm not avoiding you a lot more information. Okay, so we'll stop now. Now it is about 9:30, 9:40. 9:40, we'll come back.